Welcome dear students, I am Rajiv Lohani. Today I want to introduce to you the topic current electricity. You know that electric current is said to be flowing if electric charge flows. How electric charge flows through a metallic conductor will be our main discussion in this video. For that, we'll first understand the free electron model of metals. You know that every atom is made up of a nucleus in which there are positively charged particles called protons, and around the nucleus are distributed electrons which are equal in number as that of the protons, and these electrons revolve in different circular orbits around the nucleus. The electrons which are close to the nucleus experience a strong force of attraction from the nucleus, and as we proceed away, the force of attraction between the electrons and the protons starts decreasing. In metals, the force of attraction between the electron in the ultimate orbit and the nucleus is so small that these electrons are able to jump out from the atom and become free. When they jump out from the atom, they leave behind an ion which is positive and stationary. Every atom of the metallic piece will contribute at least one electron as free electron. These free electrons now start moving within the volume of the metallic piece randomly, just like the gas molecules do in a container. These electrons frequently collide with the stationary ions in the given metallic piece and take a definite time between two collisions. There is a certain path between or certain distance they have to travel between two successive collisions, and there is a definite time they have to take between or they get between two successive collisions. The average distance between two successive collisions of an electron is called mean free path, and the average time between two successive collisions of an electron is called mean relaxation time. The electrons move so randomly and collide with the ions so frequently that there is no resultant flow of electrons in any direction. And if we calculate the average velocity of electrons in such a case, it will come out zero. Thus we say that there is no electric charge flowing through that piece of metal, and therefore there is no electric current through that metallic piece. This situation is represented here in this diagram, in which different electrons are moving in different directions with different speeds, and the average of their velocities is zero. Now, if I establish a potential difference between the two ends of this metallic piece using an electric cell, then the electrons will experience a force of repulsion due to the negative plate of this cell and a force of attraction due to the positive plate. So their resultant average velocity will not be zero anymore, because some electrons which were already flowing from negative to positive terminal will become faster. The electrons which were flowing opposite to it will become slow. Their velocities will not cancel each other. Some electrons which are moving this way will be drifted like this, some which were moving this way will be drifted like this, and as a result their velocity when added will be somewhere in the direction of the positive plate of the cell. So electrons will have a definite non-zero average velocity when potential difference is established between the two ends of the given metallic conductor. This average velocity of electrons on applying the potential difference between the ends of the metallic conductor is called the drift velocity of the free electrons. Now we will like to find out an expression for the drift velocity of electrons in terms of the relaxation time of the electrons. For that, let us now imagine a metallic piece of uniform area of cross section A and length L. And suppose the potential difference between the two ends of this metallic conductor is V. Due to it, an electric field will be established in the metallic piece, which will be directed from positive plate or positive terminal of this cell to the negative terminal, and will be given by E equal to V upon L, where L is the length of this conductor. Because of this electric field, every electron will experience a force F equal to E into E, using the relation F equal to Q into E. Due to this force, every electron will be accelerated, and the acceleration of each electron will be A equal to F upon M, which is equal to E into E upon M, where M is the mass of each electron. Suppose there are n electrons, free electrons in this metallic conductor, and let the velocity of first electron be u1, that of second be u2, and so on, and the velocity of the nth electron is un. So u1 plus u2 plus so on up to un divided by n will be the average velocity of electrons when there is no potential difference established across the given conductor, and this will be 0. Now, after establishing the potential difference, every electron will be accelerated, and before it collides with the next ion, suppose the first electron gains a velocity v1, then it will be obviously u1 plus a into t1, where t1 is the relaxation time of the first electron, or the time between the two collisions taken by this electron. Similarly, the velocity gained by the second electron due to this electric field will be u2 plus a t2, so on and so forth, and the velocity gained by the nth electron Vn will be equal to un plus atn, so that V1 plus V2 plus V3 etc. up to Vn divided by n becomes u1 plus a tau 1 plus u2 plus a tau 2 plus so on up to un plus a tau n divided by n. I have replaced the time t by the letter tau here, which is very common in our books. So we will call relaxation time is tau. When we separate them, we get this as u1 plus u2 plus so on up to un divided by n plus a taken common because a is same for every electron, a into tau 1 plus tau 2 plus so on up to tau n upon n. This, as I have told you, is 0. So we get the average of v1, v2, v3, etc., which is called drift speed. Vd is equal to 0 plus a tau. That is a into tau, where tau is the average of the relaxation times of the electrons. Putting the value of a, we will get Vd is equal to E into E upon m into tau. This is the expression for drift velocity in terms of the electric field in the given metallic conductor and relaxation time of electrons. If I replace E by V upon L, I get Vd equal to E into V upon L into M into tau. This is the expression for drift velocity in terms of the potential difference between the ends of the given conductor and the relaxation time of free electrons.